Well, thank you everybody for joining us on the weekend after the semester is over. Today we have Dr. Ryan Green. Of course, he doesn't need any introduction, but for the purpose of being consistent with everybody, Dr. Ryan Green is currently an assistant professor in the Department of Electrical and Computer Engineering at the Mississippi State University. He received his bachelor's in electrical engineering and master's in electrical and computer engineering from the same department as he is now in 2011 and 13. And then he moved on to Virginia Commonwealth University in Richmond, Virginia to obtain his PhD in 2019. His research interests lie at the intersection of smart city communications and devices, wireless medical telemetry, and thin film antennas. In particular, he is interested in developing communication systems for 5G, implantable devices, wearable devices, and mobile laboratories. Dr. Green is the recipient of an Outstanding Teaching Assistant Award in 2018 and the Graduate School Dissertation Assistantship Award in 2018 as well, both at Virginia Commonwealth University. And most recently in 2021, he received the Outstanding Teaching Award from NSBE and Image at Mississippi State University. So without further ado, Dr. Green.
All right. Thank you very much, Sammy. As the introduction said, my name is Ryan Green. Thank you so much for coming to listen to me talk. Today, I'm going to talk about antennas for smart cities and smart health. We're going to talk about some of the concepts involved and some of the challenges. But I want to kind of follow in Chanyap's footsteps first. I kind of want to introduce myself, not just as an assistant professor, but just as a general person. So I'm a Mississippi native, born in Vicksburg, Mississippi, and I lived there from essentially birth until the end of 6th grade when my parents took jobs in Niceville, Florida. And as soon as I could get back to Mississippi, I did. And I went to Mississippi State University, got my bachelor's, got my master's. Then I worked to go for Raytheon for a couple of years in Forest, and then decided to go get my PhD at Virginia Commonwealth University, and now I'm back. So that's my education and work background. But in terms of me personally, in my spare time, I do painting. These are two of the paintings that I have done in the past. I've also got a very weird interest in popular culture, music, television, movies, as well as economics and history. And it's kind of a weird combination. But on these two particulars, I kind of want to dive in a little bit to kind of give you some background to my talk. So I want to start off with a man named Walt Disney. You may know him as the man who put together Snow White as one of the first animated full feature-length films in the 1930s. You also may know him as the man who essentially reinvented the theme park with Disneyland. Well, one of the things that not too many people know is about his experimental prototype community of tomorrow after he developed Disneyland. You may have heard of Epcot in Disney World, but the Epcot that's there is not the Epcot that he initially came up with. So essentially, Disney World's main focus at one point in time was going to be Epcot, with a theme park that was going to attract future residents. Now, what is Epcot? Now, Epcot is essentially a brand new city in terms of design that Walt Disney said that was going to address things like traffic flow, juvenile crime, pollution, crowding, all from the aspect of city planning. And just to kind of show you how prevalent this idea was in the back of his mind, that Ray Bradbury, a close friend of his, actually asked him to run for mayor of Los Angeles at the time, because Ray Bradbury thought that Walt Disney was the only one who could actually fix the traffic problems in Los Angeles. And Walt's reply to that is, why run for mayor when you're already king? Well, he kind of took this mentality and just redesigned a city from the ground up. It was going to put it in some swampland in Central Florida. But ultimately, the experimental prototype community of tomorrow was just trying to better use resources within a community to make the community more livable. And this project was reworked so many times while he was alive. And when he died in 1966, the project was pretty much all but abandoned. There's still a few things that we see that are kind of remnants of this, like in the 1980s, the mall craze was happening. That's was one of the original concepts of Epcot, of essentially having a community center that was all air conditioned. Well, moving forward to the 21st century, we now have this thing called smart cities. Now, the smart city has a few goals in terms of it's better operation of transportation, power distribution, crime detection, information systems, and community services. And you start to realize that our modern definition of the smart city, in terms of what are the aims, are not that much different than what Walt Disney had in the 1960s. The main difference, though, is that all of this is going to be not so much through city planning, but through data collected via electronic and wireless methods to assist in city planning. So the smart city is not so much a new concept as much as it's utilizing newer technology to solve older problems. And instead of using more of a company town model, it's more of a wireless network that's overlaid on top of an existing community to help make it better. Well, if you really think about what all of this means in terms of better making transportation and crime detection and community services better, we have to start looking at what exactly the goals are in particular for different sectors. So if you say a smart city to a manufacturer, they're thinking of smart manufacturing. If you're talking to someone that works in transportation, there's a certain level of, oh, we need all this wireless technology to deal with transportation services. If you talk to someone in power distribution, there's a whole different answer. So what we're starting to see is that while the smart city is a Internet of Things application, one of the things that we have to start really thinking about is not just Internet of particular things, it's really the Internet of everything, to kind of take a phrase from Steve Case. In particular, what I want to look at is just to kind of show you how prevalent wireless devices are going to be. I just want to take a look at one subsector, and that's just involving health. So let's take a look at some trends from the 1980s to 2014. Diabetes has become more regular in terms of people dealing with it and diagnosis. So we started from about 3.5 of new 3.5% of or sorry 3.5 out of 1,000 people of new diagnosis in diabetes to about a peak in 2008 of 9.5 per thousand people. And the prevalence hasn't really gone down. In 2014, we're going from, we have 8.5% of people managing diabetes as opposed to 1980, which was 3.8. But if we extrapolate this further, and even worldwide, we start to understand that this problem is not really going to get better. We're expected to be dealing with worldwide 642 million people that are managing diabetes. And all of these people who are managing diabetes are going to be using one of two methods, the test strip or the insulin pump. These are the most common ways that you can actually monitor your blood glucose, and in the case of an insulin pump, manage your blood glucose. So one of these offers a small snapshot of what your glucose is going to be at a particular time, while the other one, while it can be continuous, kind of hinders activity level and the things that the patient can actually do. So there's actually now demand for this, what's called a continuous monitoring system. So a continuous monitoring system, just shown here, is ultimately just monitors a certain analyte, whether that be glucose or something else, and that wirely broadcasts that to an access point that puts it on a database where both the patient and the practitioner can actually start looking at it. Okay, well, easy in concept, but when you start scaling this thing out along with all the other smart technology that's out there, we're talking about millions of people that will have a demand for some sort of continuous monitoring system, and possibly even multiple continuous monitoring systems, not just in their homes, but also in hospitals and clinics. And then additionally, you've got several different kinds of monitoring systems that have an ambulance. And think about all the medical devices that are existed in hospitals. So things that will better manage patient health, things that will be able to collect data a lot easier, to assist in new diagnoses and even medicine regimens. But you start to realize that with all these new devices, you're going to have a large number of wireless devices just in the medical field. So now we branch off into consumer electronics or in smart manufacturing or in transportation. And you start to realize that you're going to have thousands upon thousands of additional wireless devices, all vying for network access on the existing Wi-Fi and LTE infrastructure. Now, here's a rhetorical question. How's your cell service like on a normal Saturday in the fall in Starkville, Mississippi? I can go ahead and tell you that during a football game, or really the day of the football game, depending on the time, it is really hard to get out a cell phone call or even get internet access over 4G while there's a football game in progress and there's people tailgating. It's just because the network is just overloaded with the number of wireless devices already. But now what we're going to have is, instead of just a situation in Starkville, Mississippi, where we don't have the infrastructure to handle this, this is now going to be more continuous, where we're going to have to start gearing up to be able to handle normal day-to-day operations with all these different wireless devices and even handle an influx of people like this, just so that we can keep services moving. So with that in mind, one of the upcoming networks that was proposed about maybe 5 years ago, called 5G, started making the rounds. It made a lot of promises, very high data rates, high capacity, and massive number of devices, and longer battery life. I'll be frank, I'm not quite sure how that's necessarily going to be achieved, but it was still, a promise that 5G was going to be able to do this. Well, 5G is here, maybe not millimeter wave, but it's here. And now we're talking about gearing up for 6G, that's still going to address all these different things and make all these promises again. So with this upcoming millimeter wave boom that we're about to see, there's a few challenges that we gotta be aware of. So I've got 4 challenges that are coming up. One is going to be outdoor to indoor communication. If you've got a millimeter wave base station on the outside of a building, one of the issues is going to be reflection. So for traditional consumer electronics that need to have a certain signal to noise ratio, your building is going to cause a lot of reflection, and you're going to have a diminished transmitted wave that comes through that may or may not be high enough in signal quality to be able to provide internet access over the 4G network. So that's one thing that has to be solved. Another thing is essentially network security, which can be addressed in 2 different ways. One being the new cybersecurity research that's being performed. Another is actual physical security, where you physically separate wireless networks. In both of these cases, you're going to try and utilize your weak spots here in order to either take data in or block data from being transmitted out. A third challenge is going to be dead zone. So let's go back to this past Sunday when all the tornadoes were coming through at night. And in the center of the state, there is a Doppler radar in Brandon, Mississippi, and a relatively new water tower in the city of Brandon. And because it's placed really, really close to this Doppler radar, what you find is actually a radar shadow that's cast that's actually covering cities like Byram, where, as you probably can see, my grandparents currently live. And this was just a radar reading off of somebody's cell phone where they saw the radar shadow, but then 2 spotted tornadoes that were in that dead zone here. So if this is happening just with the Doppler radar system, which operates anywhere from 1 gigahertz to 18 gigahertz, when we start moving into the millimeter wave frequencies, we're expecting this to be even worse, on possibly even on a bigger scale because of the reflections. So here we have a simulation performed by REMCOM where they had 3 28 gigahertz 5G base stations that were surrounding a city block. And here on the right, we see essentially channel throughput, where based off of this placement of these base stations, they didn't really have any kind of channel throughput inside of the city block. And so now what you have to think about is, okay, well, if we're going to roll out millimeter wave network access, we're going to have to start putting some of these base stations inside of the city block to try and help mitigate some of these problems caused due to the reflection, which brings up the fourth challenge, and that's aesthetics. Now, this one seems maybe a little silly, but if you really think about it, it's really not. Most people do not like the look of cell phone base stations in their neighborhood. Now, I'm a little different. I'm an antennas guy. I kind of like the look of them because I understand the technology, but I understand that I am part of the minority there. Most people do not like to look at cell towers to the point where people start hiding them. So in Madison County, Mississippi, in the between Ridgeland and Madison, they actually have a cell tower on the side of the interstate that's disguised to look like an obelisk. In Claremont, Florida, they've got this really, really tall tree in the sandy soil, but that's not really a tree. That's really a cell phone. In Chicago and Brooklyn, they take their antennas and they put this brick-looking wallpaper on them to try and blend in the antenna into the environment. In Arizona, there's fake cacti out along the highway that are actually providing network access. And of course, at Mississippi State, we tend to put that stuff on top of the water towers. But you start to see that as no one really likes to look at these things. So as we're installing more and more, we have to keep this in mind, because really we're wanting a system that can actually overlay into existing infrastructure and not necessarily be a detriment to the community. So this is my proposal for that. Essentially, optically transparent communication systems or optically transparent antennas to help mitigate these dead zones that you could put in glass high rises as a method to help with the reflections and the low channel throughput. And you can put it in the middle of glass, and it can act as either an access point or a network relay station that will allow things to be able to be broadcast. So let's dive a little deeper into this optically transparent part. So the history of optically transparent antennas, there's traditionally been 2 different methods to gain transparency. One is through a mesh, which is very, very popular with things like CubeSat, where you essentially have an antenna and you put holes in it to allow light to go through so that your solar panels can actually get access to sunlight, and you can still power the CubeSat. Well, another method, which is a little bit more transparent to the naked eye, up and close, is more of thin film antennas, where you take these transparent conductors and in very thin films layer them so that they will actually be able to be seen through, but still act as a antenna. So let's take a look at the materials that are commonly used for this. One of the most common materials is called transparent conductive oxides. And this there's more prevalent than you actually think. So let's take indium tin oxide. Indium tin oxide is in a lot of things, from every touch phone of every touchscreen phone to LCD screens, to even it's sometimes used as plane cockpit windshield defoggers. And essentially, it's just a transparent conducting oxide that's based off of indium oxide, where tin is doped. And then 2 others are gallium zinc oxide and aluminum zinc oxide, which is based off of zinc oxide, where either gallium or aluminum is doped. And in particular with gallium, what you have is, here is the unit cell of a zinc oxide lattice, where a gallium atom either replaces a zinc atom or is placed in an interstitial position in the lattice. And that's how we essentially make zinc oxide more conductive. And the more and more we add, the more conductive it becomes. Well, if we take a look at how this really works, so the conductivity remains relatively constant at a certain level or a certain wavelengths here. So here's your microwave levels right around here, just to the right of omega p here. And then to the left of omega p is anything above, it could be infrared, it could be visual spectrum, but this omega p is your plasma frequency. So in essence, what we can treat this as is anything in terms of frequency lower than your plasma frequency, you can treat as a metal, but anything higher than that, you could treat as a dielectric. Meaning at visual wavelengths, you can actually calculate your transparency using this method, where you calculate your transparency as a relationship to e to the minus t over del, where del is your skin depth, and all these things are different properties of your material. You know, maybe not charge of an electron, that doesn't really change, but almost everything else is going to depend on one, the application, and then two, your material properties. So if we take a look at our doping concentration, the more and more that we add of a dopant into this, the less and less conductive it, or less and less transparent it becomes, rather, as we increase film thickness. And just to kind of show you the relationship between your concentration and your conductivity, here's essentially a conversion between these, essentially basing your transparency off of conductivity. And we find that the more conductive it essentially becomes, the less transparent it becomes. Another thing to keep in mind too is because we are dealing with thin film antennas, we have this added resistance that comes because of that thin film. So we're essentially adding in parasitic resistances that can be calculated through calculating our sheet resistance and then calculating our total resistance that is based off of the design topology. So let's say that we have a rectangle here instead of this wedge shape. If we had a simple rectangle, it's sheet resistance times the length divided by the width of that rectangle. Well, this added resistance now comes into play when calculating efficiency, because your efficiency of your antenna is going to be RA, which is your internal resistance, usually set to 50 or 75 ohms, depending on the application. And then in your denominator, it's RA plus R. So we can actually see that our antenna efficiency not only changes with film thickness, but it can also change with frequency. And the reason for this is because your sheet resistance can also be attributed to how thin the material is based off of your skin depth at that particular frequency of operation. So the higher in frequency you go, the lower your skin depth becomes, which means electrically your thin film looks thicker and thicker with frequency, meaning you're adding in less and less parasitic resistances. All right, now, because we have this inherent problem of, do we pick transparency or do we pick efficiency, we got to have some sort of trade-off or some sort of figure of merit. So I propose this figure of merit where we take our transparency and multiply it by our efficiency, because ultimately our goal is to maximize both. We want to maximize both transparency and we want to maximize efficiency. So if we do that, we can actually apply this to independent different designs. So here's two designs that I made. One is a planar dipole, and the other one is a coplanar hourglass antenna. But that's the general shape, but they're actually just transparent in of themselves. And we find that we have a resonance shift in our antenna from a design of 2.4 gigahertz to about 2.5 with the dipole, as well as lower gains than expected. So at 1.5 micrometers thick, we actually got a gain of about -3, which is pretty substantially lower compared to the gain that we normally expect, which is about 2, and a +2, by the way. And we saw a very similar result here with our hourglass antenna. And we said, well, this is interesting. So let's take a look at the figure of merit. And what we found is that ultimately the efficiency of the antenna was so low due to these film thicknesses that essentially our figure of merit just kept saying increase the number of gallium atoms that are being doped into the system, increase your conductivity at the cost of transparency, because your efficiency was just that low. It was trying to counterbalance it. So we did not. We studied that. We also studied the if these kinds of systems could actually be applied to things called frequency selective surfaces or filters. And what we found is that it's actually quite different. Is that yeah, there is some difference in our simulation of a frequency selective filter based off of material property, but it's nowhere near as drastic as something like an antenna would be, or at least a traditional antenna that involves surface currents, like you would, let's say, a patch or a dipole or something like that. And what we found is that you can design a frequency selective surfaces that's bandpass. It's still going to act as a bandpass filter, and you could design a band stop and still acts like a band stop filter. We also found too that you could possibly counter this low efficiency and this low gain with a transparent array. So here we have a 4x1 antenna array operating at 5.8 gigahertz, and we noticed that the gain went from about -3 to approximately a positive 0.5, which again is a great increase in gain. But the added benefit of having that phased array is now we can actually beam steer, which, if you're not familiar with that term, ultimately just means that we can actually change the direction the antenna is broadcasting without physically moving the antenna, just changing what phase the signal coming out of each antenna is set to. And what we found is that, yeah, we can actually beam steer with a transparent antenna, much like with a traditional opaque antenna, just with the small number of antennas that we had, maybe getting up to 45 degrees on either side of bore sight. Not so possible, but with more elements, you could actually do it. And that leads me to one of the another challenge with these optically transparent antennas, and that's really the way that they're fabricated. So these antennas and frequency selective surfaces were made using molecular beam epitaxy, or MBE, where you take a sapphire wafer and you grow your oxide layer by layer, and then you etch it away. And in total, it takes about 16 hours per antenna or per wafer to be able to get what you want. And then you have to physically hand score it, which could possibly cause damage to the antenna just to get to the point where you can test it. So I'll be honest with you, it's a little daunting to get started with something like that. So if you could move to something like an inkjet printed communication system, you can actually not only have antennas quicker, you can also have something that's a little bit more student friendly, so that you can actually teach students what optical transparency in terms of electromagnetic devices are. But you can even make bigger devices like this frequency selective surface window that this person is trying to hide behind. You can also make circuits and flexible things. So we decided to try that. So here's a joint study done by Mississippi State and Virginia Commonwealth University of making essentially an inkjet printed frequency selective surface of about 28 to operate about 28 gigahertz, and this is going to be a band stop. What we have is a P.Jet 40, which was inkjet printed here on the left, and then on the right was actually screen printed. And what we find is that P.Jet 41 is not really that optically transparent, but it's still a thin film, and it's kind of a control of just seeing how well our inkjet process is going. And we put it through the test, and what we found is that our control was actually operating a lot better than necessarily our inkjet printed sample. So again, another challenge, because our expected results essentially showed that, hey, this is passing through, everything's passing through, it should be blocking something. What gives? Well, we dug a little bit deeper and took a look at see how the thing was actually printed. There's a couple of things that are going on here. So what we find is that there's a spacing in between the drops with your inkjet printer, which results in this streaky and this streaky device that's not really consistent in terms of deposition or even conductivity. And then on top of that, you have cracks in it. But as opposed to our screen printed, which is mostly uniform, has a better result with it. So ultimately, we're going to have to go back to the drawing board when it comes to setting our printer properties for this. But it's still promising that that we can do this even with the screen printing technology. And the great thing about screen printed technology is now you can produce things on more flexible substrates, which makes it a little bit easier for deployment. So moving forward in transparent antennas, we're exploring transparent waveguide slot antennas that we can essentially put together in an array and have beamforming. But ultimately, what we were trying to do is address two different questions. One, what other topologies can we look at for transparent that possibly could counter our low gains that we see with traditional looking antennas? And then two, maybe there's something to this frequency selective surface thing where we see better results with the frequency selective surface than we do a traditional antenna. Maybe instead of having an antenna that carries current and voltage on its surface and has this larger resistance, maybe if we had a wave that was being contained by a waveguide that could then be released, but that waveguide was optically transparent, maybe we'll have better results. And moving forward with that, there's some simulations that we performed, and ultimately with a 1.5 micrometer thick material and the same conductivity as what we see in our regular antennas at 10 gigahertz, or the antennas that we saw in the previous pages, we have a maximum gain here of about 18 dBi, which is outstanding if you really think about it. And then what we took a look at then was the figure of merit. And what we see here is a very similar thing that we saw with the other antenna, which is essentially make it more conductive and you'll get a better figure of merit. But what we find, though, is that this maximum level is a lot lower and actually closer to 1.5 micrometers than anything dealing with the other antenna designs. So we're actually going to be moving forward with this hopefully over the summer and the next semester, and just seeing how it works in the real world. And of course, moving forward with transparency, it doesn't just stop at these smart buildings. With self-driving cars and 5G enabled automotive, we need to start thinking about maybe windshield embedded communication systems, as well as maybe even using this kind of technology for first responder and even military vehicles, so that we can actually avoid some site sensitivity in military communication. Now for 5G in less urban environments, I don't think I need to really kind of reiterate, but I will anyway. Here in Mississippi, we're not necessarily known for tall buildings, except maybe if you're in Jackson or on the outskirts of Memphis. But most of the time, it's a lot of rural and suburban communities. And one of the things that we really need to address is in the 5G rollout is ultimately going to be around this 18-wheeler and transit involving deliveries and goods. One of the industries that's going to be impacted by self-driving automotives is going to be the trucking industry. And that trucking industry that's going to be autonomous is going to have to be reliant on this communication infrastructure. And if we can start to see that our biggest points of entry is I-55 here in around the Memphis area, I-20 here in the center of the state, and then I-10 here at the southern end of the state. We're at the crossroads of the southeast. We have to start rolling out some of this millimeter wave stuff and not be left in the dust. And another thing I just kind of want to go circle back around to is smart health, and going back to our continuous health monitor and the monitoring of diabetes. If we delve a little bit deeper, we can find that we've got several different things that actually go into play here. We got sensor technology, we have miniaturization technology with our potentiostat, but we also have some antenna stuff that we have to worry about as well. So these are some of the challenges that I see in terms of implantronics and smart health. I want to start with the testing challenges first. And these are just practical things that if there are any students here, you probably need to be thinking about if you're interested in going into this field. If you're designing something that's going to be going inside of a biological system, being able to test it is going to be a major concern and is going to drive some sort of design choices that you make. So ports and cables, they have to go from inside to outside, and as well as whatever animal model you choose to move forward with. And different animal models are going to show different aspects of human health differently. So, for instance, the dielectric properties of skin is closer between humans and pigs than it is between humans and rats. But for things like glucose sensors, it's a whole lot. It's a little bit more of a one-to-one comparison of measuring glucose between a rat and a human. So depending on what you're testing, you need to kind of pick the right animal model for you, and then base your design off of that. This is what I call the tail wagging the dog design methodology, which is if you know you're going to be going into a certain animal model and then moving to human-based testing, you need to verify it in your animal model, and there's going to be difference between your animal model and your human model. So taking into account what animal model you're using, or the tail wagging the dog design methodology, is really important here. But in terms of design challenges, there are many. The first one is biocompatibility. So traditional materials that you would think you would be able to use are now off the table. So things like copper and solder are now incompatible with anything that you can use. It's not to say that they haven't made antennas in the past that have used copper and solder before, but they use some methods that are actually mentioned below, but you can't use those. Iron is even is a little bit weird because technically it's not bioincompatible, but too much of it and you can overdose on it. So traditionally what has happened is they will make long-term implantable antennas out of things like copper and use regular solder, and then they'll encapsulate it in a medical-based silicone and put superstrates on it to try and make it a little smaller. Well, the permittivity of the material that you're implanting your device in is so high that you can actually effectively miniaturize your antennas pretty well if you were just exposed to that material. And the superstrates in the silicone have a lot lower dielectric property than the surrounding material, meaning you're actually, while you're trying to minimize your antenna, you're actually not the smallest it could be just by method of using your superstrate and your silicone just to encapsulate it. So in comes a new material or bio materials. One of them is titanium nitride. It's highly conductive and it's biocompatible. We were talking about a cell viability of 78% over a 24-hour period. It is scratch resistant, and it's got a low coefficient of friction, and it's got the added benefit of actually being used in the medicine field before, or the medical field before, as a coating for orthopedic implants. So we take this device, we can actually make an antenna out of this, and here's just the design properties of this and our simulation. And we can actually implant it into a porcine animal model, and we find some reasonable um, methodologies here, but it's got the same problems that we find in a thin film antenna, meaning the gain is very, very low. So at 1 meter, you have a received power of about minus 65. And at 20, you're now in the signal to noise ratio. This is not that great in terms of what you can do. So there's that thin film methodology with titanium nitride. It's still got the same problems in terms of antenna efficiency as transparent antennas, with the added caveat that now we can't really do an array at these frequencies because the paramount of it is going to be, it has to be very, very, very small. But of course, we don't have to move directly into animal models for this. We've got in vitro test mimicking gels that we've developed not only here at State but also at Virginia Commonwealth. They use them a lot there, that can replicate kidneys, pancreas, fat, muscle, skin, fibroglandular tissue, all in an in vitro gel like structure. But you also at some point need to move on from the in vitro if you're ever going to get FDA approved for things like animal models. And of course, those are some of the challenges and considerations to take in when testing. But moving forward, you can actually expand your sensors to things like potassium, L-lactate, fentanyl, other opioids. It's almost limitless, because ultimately you're making a platform with your implantable device so that the sensor can be changed, but without the miniaturization of your electronics and without the miniaturization of your antenna, it's kind of stuck. You can also develop wearable tech with this. One of my personal favorites with using a transparent devices with medical is actually making a interocular eye pressure sensor that's continuously monitored. This is something that was funded through NIH about maybe 6 years ago, where someone wore a mask over their left eye and wore a contact lens, and it would actually measure interocular eye pressure for continuously. But the problem is that this will not catch on, mainly because nobody wants to wear something like this, because it kind of alerts other people that there's something wrong with it, something wrong with their health, and something that's being monitored. So taking this visible stuff and making it invisible is, I think, probably a step forward with this, and essentially incorporating something like Google Glass and just going with in the medical route with it is probably the way to go. And then, of course, Internet of Things not only does apply to wearable and implantable devices, but also things in the hospital. And just in conclusion, there's a lot of work still left to be done, a lot of many challenges coming up in the smart city and the smart health realm, especially as it comes to antennas, whether it be optical transparency or viability inside the human body. But they're fantastic challenges in which one can make a very long and healthy career out of. And with that, that's the end of my talk. I thank you so much. I'll be happy to take questions.